शुरू कर सकते हैं।
Okay, sir.
Okay.
So today I'm going to talk about nanobionics and what is and how it is changing our lives, medical field and environmental issues, how it's going to change our lives in the future. So I was motivated with the recent news when I saw in MIT news that they have successfully implemented their 6 years ago. 6 years ago, they gave an idea that we can use plants as a sensor, and now they have showed that exactly how we can sense the change in the soil, the change in the environment with the help of plants. So long back in 2016, they started this experiment, and recently they have given the demonstration also. And the person who is the main key has played the main key role is Strano, Michael Strano from MIT. So he and his team started this experiment 6 to 7 years ago, and they have not only worked in this particular experiment. They have worked in very different field, like enhancing the photosynthesis process, using the plants to take the pictures of area which is not that much accessible by the human beings. So he has carried out many experiments in the past years, and recently he is successful in demonstrating his that idea which he implemented long back. So he was the motivation, and this news was the basic motivation from my this talk. So what is nanobionics is? Nanobionics is basically the implementation of nanotechnology in the biology. So it's basically a word which is combination of nanotechnology plus biology. We can say in different fields, like in nanobionics can be used in clinical field, like in zoology, in operations and different medical problems, or it can be used as a sensor in plants, which they call plant nanobionics. Or one of the sub field of this field is bioremediation, which is basically to recover the soil which is being polluted or altered due to some environmental conditions. Those environmental conditions can be different types, means some flood area can change the quality of the soil, or due to pollution, due to factories and the water wastage is coming out of the factories, they can change the soil conditions. Or in some particular area, some people are putting toxic materials, like recent news, the exact title was spinach plant can send the emails when they detect the landmines. So basically the soil conditions can give the signal to the plant, and plant can give the signal to particular devices, so that with the help of intermediate devices we can get the information about the environments. So this is nanobionics, and with one picture we can see that how we can implement the nanoparticles or nanotubes inside the plant. So in this video you can see
placed inside of a living plant, how we can
from the
control where
back
those
side of the
particles
leaves,
go,
where the
and how they can
stomata
give it
generally
unusual
presented, we have
properties.
some pores
If you
and
want to modify the
holes
plant,
from
if you
which
want to
we
give it
can
new
implement
functions,
or
you need
send
particles that are
nanoparticles
of a
and nano
size.
tubes in the leaves, and those leaves can behave as a sensor for us. So that's how they are implementing in these leaves and the plants. So they have used spinach in their experiment, basically because it's easily available everywhere. It's not like spinach will only behave like a sensor. Any plant can work as a sensor, but they have taken spinach as their experiment. So how does it work? The same experiment which they have done, like how the soil condition the plant will detect, and how that detection we can get from the mapping of the condition of the leaves, that we will see in this video. So we have
Demonstrate
a
this
plant
process, the
which
team
is
first
having
embedded carbon nanotubes that can
nanotubes
detect
in one leaf
nitroaromatic
and which can
compounds, which
detect
are
the
often used in
nanoaromatic
landmines and
compounds
other
which always
explosives, into
available
the
in the
leaves of
landmines
spinach
or the farming
plants. These
conditions.
carbon
And we
nanotubes
have an
emit a
infrared
fluorescent signal
camera
that can be read
which
with an
will
infrared camera.
sense the
Some of the
condition of the
embedded
leaf
carbon
and will
nanotubes emit a
detect
constant fluorescent signal
the
that serves
signal.
as a
So
reference,
the
while the
left side
others
is
emit a
having a
fluorescent
constant
signal
signal
when an
from the fresh
explosive
leaf. In
compound
the
is
left side, we
detected.
have
Having
detection signal,
both makes it easier to
which is from
determine
the
if the
leaf, which is in
explosive
the
sensor
affected
has
area.
detected
So we can
anything or
compare
not.
the
They then
signals.
introduced the
So if we
explosive
put
compounds to the
some
plant's
toxic
roots. Similar to
ingredient
how
in
a
the
plant would
plant,
naturally sample from the
that will
groundwater, if there are any
go through
explosive
the xylem
molecules,
and
it takes
phloem
about
to the
10
leaves,
minutes for the plant
and
to
it
draw them
will
up into the leaves, where they
change
first
the
encounter the
condition of the leaves,
nanotubes.
and
To
that
read the
condition
signal, the
we detect
researchers
from the
shine a
camera.
laser onto the
So
leaf,
the fresh
prompting the
leaf will
embedded
not change
nanotubes
its
to emit
signal,
near
but the
infrared
defected
fluorescent
leaves,
light. This
infected leaf
light
will
can then
change
be
its signal,
detected with a
and
cheap
that signal
infrared
can be
camera
detected
connected to a
from a
Raspberry
very
Pi, which is a
miniaturized
credit
device,
card
which
sized
is basically
computer
we can make
similar
from
to
the
the
Arduino or Raspberry Pi camera. So that's that full system can be very small. We need not to have a very big or sophisticated arrangement for these type of detections. So this is very useful in wide areas or in particular areas like in transportation or in many field we can use it because it's simple to use, it's easy to carry, and it can be miniaturized in the commercial purpose. So
Nikhil.
that's how it works. That's how they have demonstrated in MIT that how it works.
Nikhil,
The second comes that
Nikhil.
how they can have the different use in different areas. So the same team, Strano and his team shows that if we
Nikhil.
incorporate a particular form of the single wall carbon nanotubes, which is covered with the polyacrylic acids, they saw that if we we know that we have stromata in the backside of the leaf, which is having small pores, and they can have two conditions, like they are closed and they are open. So they take carbon dioxide from the environment and they take out the oxygen and the water content from their leaves. If we take a solution of single wall nanotubes, we cover the backside of the leaf, it will go inside the leaf. And they saw that in a very normal conditions, the leaves and the plants are only using 10% of the sunlight energy which is falling on the leaf. But when they incorporated the carbon nanotubes, the energy absorption was increased to 40 to 49%. So that's how we can increase the efficiency of the photosynthesis process. And this is happening because somehow the spectrum of the light, the wavelength which was they were absorbing in the previous condition, that range was increased. So somehow that wavelength, which was not useful in the previous condition, now they are using that wavelength range also. So photosynthesis process was enhanced with the help of nanobionics. There are other fields also in the condition where plants are used as a sensor, like self-health monitoring. The plants can monitor their own health with the help of these implementation. Energy harvesting, like photosynthesis, we can harvest the energy in better way. Environment monitoring, we can sense from the leaves that what is the environmental condition, the change in the environmental condition, and they can send the signal to us where we are not present and we are only having plants available there. Soil toxicity detection is also can be done because there are two ways plant actually interact with the environment, either by the leaves or by the roots. So by the roots, they take the nutrition from the xylem and phloem, and if the those materials or the particles are in the same size, like nutrition size, particle size, then they can detect with the help of those nanoparticles and the materials. Dense forest informants means in some experiments they have done, like in Amazon or in the dense forest, or a very particular situation where human being cannot stay for a very long time. These plants can work as a particular informant, like how the weather is changing, how the environmental condition has changed by the time of a long period of time. So they can be very useful in such conditions where we cannot send human beings for a very long period of time. And not only plants, the nanobionics can also be used in geology side, means in the human body also. So there are many applications which already has been developed. In some areas it is fully developed, in some areas the research is still going on. So these are cochlear implants, which I will tell what is it if we don't know. Bone regeneration, nerve regeneration, muscle regeneration, and epilepsy detection and control. There are many other fields also which are still the research is going on, but these 5 fields are very much in interest because the medical field, the application in medical field is very useful in these particular 5 particular areas. So what is cochlear implant? We know that in our ear we have different stages from which we hear a sound. So first the sound will come inside our ear. In the eardrum we will get the vibrations. These vibrations will go to the hair cells, which are actually available on the front side of the cochlea. So I don't know how will I get the marker. Okay, so in the front side of the cochlea we have hair cells which will look like some stems type. So the vibration which is coming from the eardrum, that vibration will come to the hair cells. These hair cells will convert these vibrational energy to electromagnetic signals, and cochlea will send the electromagnetic signals through the nerves to your nervous system or the brain. So that's how we hear the sound. It's not exactly the sound, but sound is converting to the vibration. Vibration will convert into the electromagnetic signals, and then you can hear from the brain. So what happens when somebody will lose the hearing ability? It's only possible 70% cases only the hair cells have somehow lost their way to get the vibrational energy. They are inactive or they are damaged and they are not getting the signals, and they are not sending the signal to the cochlea, and cochlea is not able to send the signal to the nervous system. So if we are somehow able to just bypass the signal directly to the nerves, that person can hear again. But the problem is that most of the time that hearing aid is big enough to be visible from the outside. And because we need a microphone which is attached to your ear, then we need one transmitter and receiver which is directly connecting to the nerves. So this is a big device. It's not only visible from the outside, it's also need to be taken care by the person. So if somehow we can implement the nanobionics,
Graham Clark relies on electrodes to transmit electrical stimuli from an external microphone. Graham Clark relies on electrodes to transmit electrical stimuli from an external microphone. Sound is transformed into electrical impulses delivered to nerve cells. As we decrease the size of the electrodes into the nanodomain, we can provide more sites of electrical stimulation and more effective bionic hearing.
Electrodes, we can make it so small that that device is not that much visible, and we can hide it in the inside the hairs, and the taking the care of that device can be very easy. So that's how cochlear implants can be done in a very efficient way with the help of bionics. This has not been done till now, but the research is going on.
Nikhil?
The second is bone regeneration. So what happens that that regeneration with the help of nanobionics is not available and not possible for a very big fracture. But imagine that if you
now be overcome due to recent advances in micro and nano fabrication. Diseased or damaged tissue can be removed using appropriate surgical tools. A 3D scaffold that fills the defect and provides an environment for cell growth is then installed. This implant is rather sophisticated. It consists of 3 layers with a composition and structure appropriate to encourage bone regrowth, cartilage
And these 3
regeneration,
layers
and the
actually
effective
incorporating
integration of
to the
both.
regeneration of the
In the
cartilage
bottom
as
layer,
well as the
immediately
regeneration of the
adjacent
bone
to the
tissues,
bone,
and
seeding
this
with
gives a
osteoblast cells
fundamental
assists with
base
bone
for
regeneration.
the cells to regenerate.
Seeding other
So
layers in the
because
scaffold
that
with
gap was not
osteochondral
filling
cells
or
and
the filling was
chondrocytes
very slow,
then enables
but if we
production
will
of
fill these
extracellular matrix
nanomaterials, it
molecules
will give
such
a
as
mesh type
collagen that
structure
are needed to
so that the
rebuild
cells
cartilage.
can deposit on this
Cells
mesh
continue to
and
fill the
they can
scaffold, producing
regenerate
extracellular
itself in a
molecules,
very faster
ensuring
way.
reconstruction
So
of
not only
cartilage
that
and the
bone
bone-cartilage
cells, the
interface.
cartilage, which
We
is
will utilize
the
electrical
interface
stimulation
between the
of
bone structure and
nanostructured
the
electrodes
upper surface,
strategically
that
positioned
the
within the
regeneration will
scaffold
be
to
very fast
facilitate the
if that
regeneration
damage or the
process.
tissue damage is
The
very
ideal
small.
outcome
So
is
not in big
complete
picture,
repair of
but
the
if
damaged site with
the
functional cartilage.
damage is very
In this
small, the
application,
tissue damage is very small, we can regenerate with the help of these materials very easily. The same way, if there is a damage in nerves,
that support and
the
facilitate
nerves
cell
are
growth
not
opens
able
up
to
the
regenerate
possibility of
because they
developing
don't
a
have
conduit
one
for
seed
reconnecting
or
severed
one base
nerves. We have
to
recently
grow again.
demonstrated
But
that
if we
nanodimensional
incorporate some
topographical
type of
cues can be
nanotubes
used to control
which
the
will
direction
give
of
them
neuroid
a bridge
outgrowth.
to connect
This
that
provides a
the
platform for
damaged
nerve
area, we
regeneration
can easily
or for
regenerate
coupling
with the
nerves to
help
a
of
neurally
these
driven
materials
prosthetic,
if these
such as a
materials
robotic
are
hand.
biocompatible. So nerve regeneration has been done already in medical field with the help of nanotubes, and it was very easy for the period of time, and that it was very fast. The how should I say, the recovery was very fast with the help of these materials. The similarly, if somebody goes through an accident,
A number of diseases
due
and,
to
of course,
if he
trauma
is
can
damaging
lead to
its
muscle loss and a
muscles,
need for muscle
and if we
regeneration. We are
incorporate
developing electromaterials that provide an
some
environment for
electrical
muscle
cells,
cell growth.
they call it, the regeneration
Nanotopographical
of these
features
cells
on
is
these
very pretty
platforms
fast,
direct the
and
assembly of
with
the
the help of
individual
same
cells
type of
into muscle
nanotube which is
fibers and tissue.
biocompatible,
We
these
envisage that this
muscle
regrown
growth
tissue can
is
be
pretty fast,
transplanted into
and
an
the
environment
damaged
where muscle
area
regeneration
it
can
will
occur.
get recovered in a very fast period of time. So these regenerations are very useful in the medical field because that time period of the recovery is very important, because in that same time period, the body is getting affected due to the other problems also. The other field which is very useful for the patients which are having epilepsy and they are getting seizures. So what is the problem in this
One in three of these
this
individuals
type
are
of
untreatable
disease,
using conventional
that
approaches.
when people
We are
will get
involved in the
seizures,
development of nanostructured
previously either
electromaterials
they are
as a
not
critical
getting the
component
signals
of
in
an
the correct
implant
time,
for
or
epilepsy
they will have
detection
to
and
take the
control.
medicine
We propose to develop
sometime
an
even
implant that
if
will
they
be
are not going
capable
to
of
happen.
detecting brain
Means they are
signals
not
to
going
provide a
to get the
warning of an
seizures, but they will
impending
have to take
seizure.
the medicine in advance.
Integrated
So if
into that
we put
implant will be a
some
nanostructured
kind of
polymer
device, the
network
nano
that
device,
functions as a
which
reservoir
will
for
sense the
anti-epileptic
from
drugs.
the nervous system
Coupling the
on
electronic
from
warning
the
system
this
using
network,
electronic
that
signals
they can sense the
arising from the
seizures
brain will
conditions,
enable triggered release of the drugs
that drug
when
or
and
that
where
the
they are
medicine,
needed,
it
hence
can be
preventing
given
seizures from
in the
occurring.
efficient time, and unnecessarily the patient need not to go through the medication. So these type of implementation can really help the patient not to unnecessarily take the medicine, and whenever it is necessary they do not miss the medicine. So these type of devices, they not only sense, they can also use as a reservoir for the medicine. They can give the medicine of a particular time also. So they can as work as a sensor, they can work as a what should I say, to give the medicine to the patients also. So these are the fields which are being used in the field of nanobionics recently. So the medical science as well as the biology as a sensor in the plants, we can use nanobionics in the recent area. Till now, these sensors are not developed very frequently. Only scientists have given the experimental verification, especially in MIT. But slowly, the commercialization of these sensors have also started, and I'm sure that in coming futures, as soon as we will get some saturation level of the conventional sensors like solid state devices and the sensor, these sensors will grow pretty fast. So these are the references from which I have got this information. MIT News time to time give the steno team information. And I have seen some videos in YouTube which are connected to these developments. Thank you.
Okay.